Okay, I want you to just close your eyes for a second. Picture the most, I don't know, the most complex physical object you can imagine.
Hmm.
And I'm not talking about a Swiss watch. I'm not talking about a Ferrari. I mean something the size of a small city. A massive chemical refinery maybe, or a gigawatt power station. You're standing there in a muddy field, and your job is to build this thing.
And
And
just to raise the stakes a little, building this thing means you're dealing with millions of liters of explosive fluids, high voltage grids, toxic gases,
and people.
and about 10,000 people all trying to work together without, getting hurt.
Exactly. It is chaos waiting to happen.
Yep.
If you miss one detail here, you don't just lose money, and you will lose a lot of that.
Oh, yeah.
You could have an environmental disaster on your hands.
Mm.
So the question is, how do you stop it all from collapsing into disorder before you even break ground? You don't start by pouring concrete. You start with a list.
A very, very specific and frankly kind of an intimidating list.
And that's what we're digging into today. We are looking at the brain, really, of a mega project. We've got a set of documents here, specifically labeled EA9 and SB17 E4.1. Now, on the surface, I'll be honest, they look dry. They look like a table of contents for a boring engineering report.
Mm-hmm.
But if you actually read them, and I mean, really read what they're asking for, this is the source code. This controls the reality for $1 billion facility.
That sounds dramatic, but it's not wrong. It is accurate. What we're looking at is the feed index. And if you understand this document, you understand how the modern industrial world gets built.
So before we get lost in all the acronyms, because there are going to be a few, let's just unpack that first one. What exactly is feed? Because source SB17 defines it pretty rigorously.
Right. So in life cycle of any massive project, you have the initial idea, and then way down the line, you have the actual construction where sparks are flying.
The fun part.
The fun part, exactly. Well, FEED is the bridge between them. It stands for front-end engineering design. And the document, SB17, it puts it very clearly. It says this phase provides the technical details such as specifications, design bases, technical requirements, and drawings.
And it says these form the basis for the contractor's detailed design.
Hmm.
So just to be clear, this is not the final blueprint where every single bolt is drawn, right?
No, and that is a crucial distinction. FEED is the set of instructions for the people who make the blueprints. It defines the scope. It's the what and the how before you ever get to the build.
And if something isn't in the feed package?
The contractor isn't going to build it. Or, more accurately, they aren't going to price it, and then you've got a massive fight about money 2 years down the road.
Which nobody wants. And that is why this index document, EA9, is so fascinating. It's the typical feed index. So it's a checklist, really, of every single document that has to be written, approved, and stamped before you sign that huge construction contract.
It's a risk management tool disguised as a spreadsheet. It forces you to think about problems before they even exist.
So let's break down how that risk management actually works. The document is organized logically, starting with Part 1, General Information. And the first thing that jumped out at me wasn't the technology. It was the geography.
Context is everything. You can't just copy-paste a refinery design from Texas and drop it in, say, Norway.
The index specifically demands meteorological and site data and local information site and country. Oh, that seems... Well, it seems basic. Obviously, you need to know where you are. But walk me through the implication there. Why is this line item number 1?
Okay, think about the physics of the environment. If you're building in the Middle East, you need these massive cooling towers because the air itself can be 45, 50 degrees Celsius. Your motors need to be rated for extreme heat.
Right.
Now, take that same plant design to Siberia. Suddenly, you need trace heating on every single pipe so the fluids don't freeze solid. You need special steel that doesn't become brittle in the cold.
So if you miss that meteorological data line item,
you design the wrong plant. It literally won't work.
So the index is forcing you to look at the sky and the ground before you even look at the steel. And then right below that, in Part 3, we hit what I'm calling the rules of engagement. The section is titled Regulations, Standards, and Specifications.
This is the bureaucratic backbone of the entire project.
It's not just a grab bag of rules, though. There's a hierarchy here that I found really interesting. The document lists statutory regulations, then national and international standards, then employer standards, and finally contractor standards.
Yes, and that order is absolutely not an accident. It is a hierarchy of power.
Okay, so let's play out a scenario. Let's say the employer standard, the big oil company paying for the plant, says, we want this safety railing to be 1 meter high. That's what we do at all our plants. But the statutory regulation, the local law where they're building, says it must be 1.2 meters.
The law wins. Always. Statutory regulations are at the very top of the food chain. But here's the catch, and this is why the index matters so much. If you don't identify that conflict during the feed phase, you might order 5 kilometers of railing that's 20 centimeters too short.
And then you're scrapping tons of steel and delaying the launch.
Exactly. You're just burning cash. This index forces you to gather all those conflicting documents, the laws, the ISO standards, the company rules, into one room before anyone draws a single line. It makes compliance the foundation, not an afterthought.
Speaking of things baked into the foundation, there was one entry in that general information section that actually surprised me. Section 2.5 is just one word. Ergonomics.
Ah, yes,
Yeah.
the human factor.
Right. I mean, when I think of these big industrial engineering documents, I'm expecting PSI, voltage, steel grades, concrete density. But here, right at the top, basically on page 1, alongside health, safety, and environmental, we have the study of how people sit in chairs and reach for buttons.
It is a critical insight, and it's one that's often overlooked by people outside the industry. Look, you can design the most efficient, high-tech pump in the world, but if the valve to turn it off is located 3 meters in the air or, behind a scalding hot pipe, a human being cannot operate it in an emergency.
So the system fails because the human fails.
Precisely. The feed index elevates ergonomics to a primary category. It's acknowledging that the human operator is a component of the system, just like a compressor or a turbine. The engineers have to produce an actual document proving that the control room lighting won't cause glare, that the alarms are audible but not deafening, that the valves are reachable.
It's comforting to know that amidst all the megatonnage, someone have to write a report about whether the chair is comfortable. Okay, let's move from the humans to the heavy machinery, the meat of the project. Part 4, Design Dossier.
This is where the abstract rules start to turn into physical reality.
The list of requirements here is just so visually evocative. You have site plans, plot plans, and something called hazardous area classification documents.
That last one sounds like a movie title.
It is probably the single most important safety document on the entire list, hazardous area classification. It essentially creates an invisible map of the plant. It defines zones where explosive gases might be present during normal operation or, in an accident.
So it's a map of where the danger is.
It's a map of probability. If a zone is classified as hazardous, let's say Zone 1, it means explosive gas is likely to be there. And that determines everything you can buy. Every light bulb, every motor, every phone, every sensor inside that zone has to be explosion-proof or intrinsically safe.
Which I assume is significantly more expensive than the stuff I'd buy at the hardware store.
Orders of magnitude more expensive. So if you get this document wrong, 2 things can happen. If you overclassify, you mark safe areas as dangerous, and you burn millions of dollars on unnecessary specialized equipment.
And if you underclassify, you put a standard light switch in a gas cloud. Someone flips the switch, it creates a tiny spark, and the plant explodes. The feed index demands this document is finalized early so everyone knows exactly what the safety constraints are.
High stakes for a PDF. But here's where it got really interesting to me, just from a structural perspective. I started scrolling down through Part 4. Part 4.3 through 7 are process units, so that's the chemical reactors. Then Part 4.8 is power systems. Part 4.9, utility systems. And I noticed a pattern.
You saw the repetition.
It's almost cut and paste. It felt like, Groundhog Day. The list of required documents for the power system is almost identical to the list for the process units.
That is the discipline of systems engineering in action.
But do we really need a control narrative and a cause and effect diagram for the water treatment plant? I mean, I get it for the nuclear reactor, but for the water tap?
Oh, absolutely you do. Because in an integrated facility, everything is connected. Think about it like a row of dominoes. If the boring utility system fails, say the cooling water pumps stop working, what happens to the main reactor?
It overheats.
It overheats immediately, the pressure spikes, the safety valves blow, so a failure in the utility is a failure in the process. The index applies the same rigor to every single system to prevent those weak links. It doesn't matter if it's water or electricity or feedstock. The documentation standard is identical.
Let's unpack one of those recurring terms because it appears everywhere in the list. Instrumented protection function narratives. That is a mouthful of jargon. What is that actually telling the builder to do?
Let's just break it down. Instrumented means we're using sensors and automatic valves robots, essentially.
Okay.
Protection function means safety stopping a disaster. And narrative implies a story.
So it's the story of how the robots save the plant.
That is a great way to put it. It's a logic document. It says, if pressure sensor A sees high pressure, then logic solver B must tell valve C to close within 3 seconds. It's the script for the plant's immune system.
And the index requires this script to be written for everything.
Yeah.
Power, water, chemicals.
Yes. By forcing every unit to have these instrumented protection function narratives, you ensure that the safety logic is consistent. You don't want the power plant safety system written in a different language than the reactor safety system. When an inspector picks up a safety file for the generator, it should look exactly like the safety file for the compressor.
It reduces the cognitive load.
Exactly. You do not want creativity in safety documentation. You want boredom. Boredom means predictability, and predictability means safety.
Boredom means safety. I might have to put that on a t-shirt. Now, when we think about these big plants, we usually focus on the skyline, the smokestacks, the big tanks. But the feed index has a way of highlighting the things you'd normally ignore. The infrastructure.
The veins and arteries of the site.
Yeah. Section 4V12, paving, roads, and fencing. Seems so mundane, but it's on the list. You actually have to design the fence.
And not just the fence, but the roads themselves. Imagine you need to deliver a 500-ton reactor vessel. It comes on this massive transporter with 100 wheels. If you haven't designed the road width and the turning radii correctly back in the feed phase, that vessel gets stuck at the gate. You can't just wing it with a 500-ton load.
And then there's Section 414, HVAC, heating, ventilation, and air conditioning. Now, in my house, HVAC is about keeping the bedroom cool so I can sleep. But in this document, under HVAC, there's a requirement for a process safeguarding flow scheme.
Yes, that caught your eye.
It did. Why does the air conditioner need a safeguarding flow scheme? That sounds like military terminology.
Because in an industrial environment, HVAC is not about comfort, it is a life support system. Imagine there's a toxic gas leak outside in the plant.
Okay, scary thought.
The people are sheltering inside the control room. You need the HVAC system to instantly detect that gas outside and shut the intake dampers to seal the building. It needs to pressurize the room so gas can't leak in through the cracks.
So the AC is basically acting like a submarine hatch.
Exactly. Or, conversely, if there's a fire inside the building, you might need it to ramp up and purge smoke so people can see to escape. The HVAC has to talk to the main safety system. That's why the index treats it with the same respect as a chemical reactor. It's a safety-critical system.
That is wild. It really shows how interconnected everything is. The list also mentions telecommunication systems and something called analyzer houses in Section 4V17.
Analyzer houses are fascinating. They're basically small, high-tech laboratories dropped right in the middle of the pipe jungle.
And they have their own equipment lists in the index.
They do. These are little buildings packed with chromatographs and laser sensors that are constantly sniffing the chemicals in the pipes in real time. They're the robot noses of the plant. The index ensures that these aren't just treated as accessories. They are complex facilities in their own right, needing power, data, carrier gases, and yes, their own HVAC safety systems.
And you can't skip the electrical side. Section 4E8, power systems. The sheer density of requirements here is overwhelming. Single-line diagrams, electrical protection diagrams, and one that sounded almost poetic, specification earthing cabinets.
Let's talk about earthing or grounding. It is one of those things that is completely invisible until it kills you.
High stakes again.
In a facility with high voltage and flammable gas, static electricity is a bomb. If a lightning bolt hits a tower or a motor shorts out or even if fluid rushing through a pipe builds up a static charge, that energy needs a place to go.
And you want that place to be the ground, not a person.
Exactly. You need a guaranteed path of least resistance to the earth. The earthing cabinet is the central hub for that protection. The index demands you specify it now. You don't just figure it out when the electrician shows up. If you don't design the earthing grid correctly in the feed phase, you are building a lightning rod without a wire.
So we've designed the plant, the safety systems, the roads, the earthing. But we need to look down, way down. Section 4V10, site preparation and leveling.
The phase before the face.
The document lists geotechnical investigations, basically poking the dirt to see how strong it is, and soil remediation. That implies the dirt might be dirty.
In many industrial zones, you're building on what are called brownfield sites land that's been used before. Maybe there was a factory there in the 1950s. The soil might be soaked in oil or chemicals. You have to clean remediate that land before you can put new foundations on it.
And that's expensive.
Incredibly expensive. If you don't account for that cost in the FAE, your budget is blown on day one.
But the thing that really stopped me in my tracks, and I actually had to double check this to make sure I wasn't misreading it, was in part 6, site data. It lists the usual stuff: soil investigation, Matoshan data, but then item 614, archaeological investigation data.
Yes, that is a fascinating inclusion in a technical engineering document, isn't it?
Imagine this. You are building a futuristic energy plant, billions of dollars of cutting-edge technology. And one of the very first boxes you have to check is, did we find any ancient pottery?
It connects the future directly to the past. But think about it from a strict risk perspective. You start digging foundations for a massive cracker unit, and your excavator hits a Roman settlement or an indigenous burial ground or a medieval wall.
Everything stops.
The project stops immediately. The police come, the universities come, the lawyers come. You could be delayed for 6 months, a year, maybe indefinitely.
And in the world of mega projects, time is money.
Millions of dollars a day. So the FEED index forces you to do that investigation before the bulldozers arrive. It's essentially saying, go look for the pottery now, while it's cheap to move the design so we don't lose $100 million later.
It's a reminder that these projects happen in the real world with real history, not just on a computer screen. Speaking of the real world, let's talk about existing stuff. Part V5, existing facilities.
This is crucial for those brownfield projects we mentioned, where you're building next to or on top of an old plant. You need the design books and drainage details of what's already there.
It's like doing surgery. You need to know where the patient's existing organs are before you put in the new one.
That is a great analogy. You need to know the process flow schemes of the old plant to tie in the new pipes. If you assume a pipe is there and it's not, or if you connect a new high-pressure pipe to an old low-pressure pipe, well, we are back to explosions.
It seems like explosions is the recurring consequence of ignoring this index.
It usually is.
Okay, so we've covered the content of the list, from the soil to the stars. But I want to pivot for a moment to talk about the format of the list itself. Because Source EA9 isn't just a static piece of paper.
No, it's a tool. It's a living thing.
Section 3 of EA9 explicitly says, the MS Excel file of the typical feed index is embedded in this document. And it knows that the consultant, that's the builder, can use this file as the basis for the project-specific feed index.
This is a key administrative detail. It admits that the PDF is just a snapshot. The real work happens in the spreadsheet.
Why does that matter? Why is the Excel format so important?
Because feed is a negotiation. You start with this template source EA9, which lists everything. It's the perfect list. But no project is perfect. The employer and the contractor sit down and they start deleting lines or adding lines. We don't need a cooling tower, delete that section. We need extra security because of the location, add this section.
So the spreadsheet evolves into the customized plan for that specific project.
Exactly. The document says the index is indicative and shall be adjusted. It's living. But once that adjustment is finished and everyone agrees, it hardens. It stops being a draft and it becomes law.
And this connects to our second source, SP17. It mentions something called the Contract MDL.
The master document list.
Right. It says for the Contract MDL, the feed documents are included by reference.
And this is the transformation. The Excel sheet stops being a planning tool and becomes a legal weapon. Once that list is attached to the contract as the MDL, it defines the payment milestones.
So if a document is on that list,
the contractor must deliver it to get paid. It's binary.
right.
If the safety relief valve data sheet is on the MDL, and you haven't submitted it, you don't get your check. It doesn't matter if the valve is physically installed on the site. If the paperwork isn't done, the job isn't done.
Wow, that is a powerful shift in perspective. The index is the product. The physical plant is almost secondary to the documentation that proves the plant is safe and legal.
In the eyes of the law and the insurance companies and the bank, yes. The MDL is the bill of sale. Without the certificate of conformity, the steel is just scrap metal.
It's amazing how much power is hidden in a simple list of files. We've gone from seismic investigation data deep underground to telecommunication systems in the air. We've looked at statutory regulations and specific control valves.
And we've seen how these very specific technical documents like that instrumented protection function narrative form the nervous system of the entire facility.
It really changes how you look at a factory or a refinery. You drive past these places and you see the steam rising, you see the massive tanks, the lights at night. It looks like a triumph of steel and chemistry. But the reality is, that physical structure is just the 3D printout of this document.
That is the perfect way to summarize it. The feed index is the DNA. If the DNA has a mutation, a missing line item, a wrong standard, the organism will be deformed.
And it's not just about building it, it's about operation. We talked about ergonomics, about HVAC safety. This document is trying to predict the next 20 or 30 years of life inside that plant.
It is attempting to create certainty in an uncertain world. It creates a closed loop where every risk, from the soil quality to the operator's chair, from the archaeology to the earthing, is accounted for before a single dollar changes hands.
So here's the thought I want to leave you with today. We often celebrate the person who cuts the ribbon. We celebrate the architect who sketches the beautiful shape of a building on a napkin. But maybe the real genius of the industrial age isn't the steel or the chemistry. Maybe it's the ability to organize 10,000 tiny, disconnected details into a single, coherent list before the ground is even broken.
It's the invisible engineering of information.
Exactly. If you controlled the index, would you control the reality of the project?
I think the answer clearly is yes.
Thanks for diving deep with us today.
A pleasure.
We'll see you in the next one.
If you're interested in the templates, please visit our shop. The link is in the description.
Thanks for watching. Please subscribe and see next time.